As the question says, consider the situation shown in figure. The system is released from rest and the block of mass 1 kg is found to have a speed 0.3 meter per second after it has descended through a distance of 1 meters. Find the coefficient of kinetic friction between the block and the table. Now in this question they have given us the initial velocities as being 0 because the system started from rest. And finally, when this block has descended by 1 meter, they have given us the velocity of this block to be 0.3. Obviously it will be downwards. Now if this is 0.3 and then there will be the velocity 0 for this rope because this has been tied at one end to the ceiling, so it won't be moving. So the speed of this string, that is the part of this string over here, will be twice of this. So the speed of this will be to the right 0.6. Right? This you must have learned from the pulley equation, the same as we had the acceleration relation in the pulley equation. So for this, if we consider this to be block 1 and this to be the block 2, then we are having the M1, M2. So now we have been given the distance, that is, we can easily find out the work done by the gravitational pull over this block. Now we can also find out work done on this block in terms of mu, which we need to find out. So it is quite clear that we can somehow apply work energy theorem over here, because velocities are also been given here. So let us proceed with that only. This actually gives us the idea that we should employ the work energy theorem for this question. You must all be knowing that work energy theorem is the total change in the kinetic energy of the system equals to total work done upon the system. Right? So we can write it here as the change in kinetic energy of the first block, that is half m1 v1 square minus 0 plus for the second block half m2 v2 square minus 0 and the work done. Now work done will be due to two forces. First is the gravitational pull. Since the movement is downward, that is in the direction of the force, the work done will be positive. So it will be m2 g h, where h is the distance moved downwards. But the frictional force will be in the opposite direction. So it will be having a negative work done over the system. So it will be minus mu n, where n is the normal reaction, into s, where s is the displacement. Putting the values over here, we get half into m1, that is 4, v1 square, that is 0.6 square, plus half m2, which is 1, v2 square, that is 0.3 whole square, equals to m2, which is 1, g, that is 10, and h, that is 1, minus mu, which we need to find out, n, which is simply mg over here, so it is 40, and the distance s, that is actually 2. Why it is 2 is because this is moving a 1 meter downward. This is moving no distance. So obviously this will be coming down by 2 meters. Just have a little bit of idea that some of its length will actually be required to balance this length. So it will be obviously more than this one. And this we have the exact relation we have found out by the pulley relation. So here is an equation we are having only in mu. So we can solve out mu from this expression, giving us 9.235 over 80, that is approximately 0.12.